But welcome everyone to the July monthly meeting, which is still hybrid because of all of your wonderful responses back to us trying to cancel it. So thank you. We appreciate the feedback. It is very well encouraged, and we just like hearing from all of our members. So thank you. Thank you very much. Tonight's background is from Doug Neverman, yes, which is in the house. And he actually took that with a scope with a telescope in Australia. He rented some time down there so he could get the southern object, which is the I don't think I wrote it. What is it? Oh. Lobster or War and Peace Nebula, which is also NGC 6357. So if anybody ever goes down to more of a southern hemisphere, there's your challenge. But it looks beautiful. You did a great job. I'm in the wrong screen. So there we go. Tonight, this is your board, which I know we show it every single night, but for the new faithful out there, me, obviously, and then we've got the VP, secretary. Dave's not here, but he's hopefully online tonight. But John's
I am.
Yay! I love everybody chiming in. It's beautiful. Although it seems like we have some feedback.
I'm working it.
Okay. Matt is also our techie AV person, trying to do the best he can without having any official training. Just kidding. Lifetime of training, yes. Conrad, I don't know if he's online.
I'm online.
Perfect, thank you. And Ahmed is here in the house because I know he's here. So I thought I would throw in a little bit of an agenda that we're going to go through just in case anybody wants to know what we go through every single night. I'm not going to read everything because we'll get to that. But I did want to show off Mark's Able 39 photo, which I thought was really pretty. So I don't know if he's on tonight. He was supposed to be, but maybe not.
I am here.
Yay. And now for my favorite point of the beginning of the evening is welcoming our new members. We have 10 new members. And is there anyone in person here that is new? That's okay. Is there anybody online that is new? If you are, just put in chat, if you can go down to the bottom and put in chat that you are a new member. That way we can say hi and welcome to you. We also have two people that are coming back. So that is awesome. So thank you very much for returning back to the MAS. And like as Matt said, we have the 693 total members, and there's the breakdown for that, along with Conrad Sanders' pinwheel galaxy photo that he took just recently. So I appreciate everybody letting me take their photos and show them off, which we'll talk about a little bit more for showing off for people tomorrow or for next month. So excellent. And then we have our sky in the next month. I heard from you guys that you liked this, so hopefully I did you justice this month. I might at some point change the moon picture, but I like Fultz's picture. It's beautiful. I did add on the sunrise and set, and I think we're at about 15 hours of daylight now, which is not great for us for people going out and viewing, but it's summer. What can you do? And then we also have down toward the bottom the Delta Aquariid meteor shower. So I'm hoping to get out and look at that. And since it's the first quarter moon, it should be pretty good to see. But if anybody does capture some shots of that, we'd love to see that in next month's. What, Suresh? So meteor showers is one of those things that you can take pictures of, and submit it to our August meeting so that we can all take a view of it. So we'll get there. And up next, we have our Loner Scope program with Antone Gregory. I don't know if he is on tonight to talk a little bit about the Loner Scope.
I am here.
Excellent. I will turn it over to you then.
Okay, we have our Loner Scope program, of course. Members can borrow one of our 18 instruments for a month at a time. It's a very popular program. Our 47th loan of the year just left my house about 2 hours ago. Members can request a telescope by going online under Members and Loner Scope program, and you'll see an easy to fill out form there that will send the message to me, and I'll make arrangements with you to come and pick up your telescope at my home. We also have great courses, CDs, there they are. Those are underused, but the few who have used them have given them very good reviews. Back to you, Trina.
Oh, there we go. I was trying to get myself unmuted. Thank you, Antone. Do we still have some of those that have been still in their plastic wrap?
We do have some that have never been used. Yes.
Oh man, we should promote those a little more. But they're very good courses. I mean, you can listen to them while you're doing things around the house or in the background as you're processing photos. They're very, very nicely done. It's same. The question is for anybody online, how do we get the great courses? And it's the same link that you take from the member forums, or not forums, from the member website to request a telescope. They're just a little bit farther down on the list. So you just scroll through there, still enter your name and information, and say which one you want to try out, or a couple of them. And if you can keep them for 30 days, or if you need to, you can keep them for a little bit longer. So they're not widely used, but they are very good. I've done a couple of those. So, and I believe most of these were, some of these were donated by Father Brown. So they're donations that have come to us, I believe. Upcoming star parties. We have the star party at ELO this coming Saturday. So in 2 days, head on out there and take a sight to see. We also have the BSIG that is happening at the same, in a different location. But that's fine. It's different interests for different people. And then later on at ELO, we do have the Camping with the Stars. That is something that you can sign up for as far as camping, camp on the ball field, and or in the park. But I believe it is free to attend. No, $10. Sorry. Thank you. But it's got some great speakers and just a nice weekend away if you're interested. We also have CGO that's still open. The BAT is available to be used. LLCC we'll talk about in a little bit for the Northern Night Starfest. But we also do want to mention that CGO is having their imaging rig training on the 15th, provided it's clear skies. Otherwise, it might switch to the 14th. Correct? Okay. All right. Now for the LLC update, I will invite Ken Hugil up here. Yay!
All right. Name's Ken Hugil. If people don't know me, I'm the chair for the Dark Sky site, known as LLCC, stands for Long Lake Conservation Center. We have a joint venture with the Long Lake Conservation Center where we can house our telescopes up there. They allow us to come up for 2 weekends a month, Friday and a Saturday night, and stay overnight. There's dorms that we can stay in, showers in the dorms. They do not provide food for us. You're on your own for that, but the accommodations are pretty good. And the skies are really dark. Up there we have a 25-inch and a 30-inch Dobsonian. You can see them in the pictures there. Both have servo cats and digital setting circles on them. So you can either just run it with the digital setting circle, or you can use it with the servo cat, or just manually if you want. We have an 8-inch Dob up there, some 20 by 80 binoculars that you can use. And it's up by McGregor, Minnesota, if you know where that is. And on our website there's a link down below. If you go out there, there's a lot of information on the LLCC on our webpage. So you can go and find that. Let's see, do I just hit the space bar here? Okay. So right now the committee has some various projects going on. Some of the ones we're working on this year is the 30-inch scope. For years have had kind of a cooling issue. We always kind of thought that the mirror was a little soft, but it's actually just that it takes forever to cool off. And we always have good views early in the morning through it. But, you know, early on in the evening, it always seems like it's kind of soft. So we're looking at how we can do a better job of getting that mirror cooled down. The 25-inch servo cat has had some intermittent issues reported earlier this spring. So we're going to take a look at that and see what's causing that. We've got a cable on the 30-inch servo cat that frayed on us. We bought a new one. We put it on at frayed. So we got another one on order. We're doing that. We got money in the budget for a new door keypad for replacement of that. Volts is installing the dark sky meter up there. So we'll have dark sky meter readings throughout the year. We got a new finder for the 25-inch that we'll be mounting on the 25-inch. And the 25-inch also, we swapped out the Argo Novice that was on there because it stopped working, it died. And we put in a Nexus DSC. So we're writing some new procedures on how to use that. And so far, everybody likes it a lot. I know it's a little bit different. It's different from Cherry Grove, different from the ELO, but it seems to be well liked. So, and then the last one, what did I put on there? Oh, observing field Wi-Fi. We want to research if we can get Wi-Fi out on the observing field up there. So those are kind of the projects we've got going on. Any questions? Nope, just clapping. Northern Night Starfest, or I guess it's known now as Northern Nights Smoke Fest, but this year we're hoping that the Canadian fires die down before then. Some reasons of why you should go. You know, once again, we got access to the 25 and 30-inch. There's some great views of eye candy that you can get through there. Daily lectures. And I'm going to do my Father Brown impersonation. We need people to volunteer to do daily lectures. We need, right now, I think we only have one lined up. So if anybody wants to volunteer or comes up with anything they want to talk about, it's ATM, it's astronomy, it's astrophotography, you know, whatever, basically. It's like an hour presentation during the day. And you get $50 for doing that. So if anybody wants to give a daily presentation, we need it. There's hiking, canoeing, biking, nature walks. The food is usually pretty good. We got dark skies. The camaraderie is great. Last year it was raining, so we had a bonfire. That was the first year we ever did a bonfire. We had a great time. Swap Fest, prizes. We give away prizes. There's a picture of Jerry winning some binoculars. We got a yearly observing list that Greg puts together, and then of course the midnight snack. I
have a question
Yes.
on the need for speakers. They don't have to do it every single day, though.
No,
do they?
just
It's
one lecture. Anytime. It could be Thursday, Friday, Saturday, Sunday.
Okay.
Usually in the afternoon, like 1, 2, or 3 o'clock. So
Okay, great.
Yep. Yeah, Bob King is signed up as our featured speaker on Saturday, and he's going to talk about, I think, the aurora. And he's going to talk about the aurora. John Marchetti, if you're online, he's lining up hopefully some other speakers for us for featured speakers at night. I think that's my last slide, actually. Oh, no, I do have one more. Yes. Yeah, well, we can do Zoom. And even with, if we could get a professor from the University of Minnesota that doesn't want to drive up there, we can do Zoom. Nowadays they have fiber internet up there now, so we got good reception. So Zoom is a possibility. And it might be easier to get, the better lectures that way. Astronomy camp. The Long Lake organization up there is, what they do is they bring kids in middle school age and stuff during the year and teach them about nature and, take them on nature walks and all that stuff. So that they've decided to put on an astronomy camp this year for middle-aged kids 10 to 15. And they've asked us to help. And so they're asking us for one daytime lecture. And then they're asking us for like a project, a hands-on project, like maybe make a star wheel, or something like that. And then they've asked us to come and do a star party either Monday through Thursday. Just one night is all they wanted, but we have to kind of play it by weather. And so we're looking for a couple volunteers for that. And they'd provide free food and free lodging for anybody that volunteers, for this. And then MAS, we bought some red flashlights to give each of the kids. And then in our budget, we have $1,000 donation. It's about $400 for a kid to go. So that would cover a couple kids as a, scholarship for them to go to the thing. And so I think that's about it. Any other questions? Want me to back up, Katrina, or is that okay?
That's it.
All right.
All right. Thank you very much, Ken. I
Thank-
appreciate it. I have a hand though. How many people have been to Northern Night Starfest? About 75% of you in the room. Have you all enjoyed it? Yes. Resounding yes, even though sometimes it's been a little clouded out. Right. Veltz was just saying that the registration is open and active right now. You just have to go out to the calendar on the MAS website and follow that out to link. There's, I think, a $50 registration fee, but then you can, plan for your rooms with boarding, sharing a room with somebody else and signing up for the food. Because they do provide, I think, brunch, breakfast, and dinner. No breakfast, brunch and dinner. You think you're brunch on Monday? Okay. Okay. Okay, but that is an extra cost, but at least there's also the dinners too. So, and there's a midnight snack. Yes. Yep.
I have a question.
Mhm.
Ken, did you want to mention the honorarium?
The honorarium,
Yeah, so I guess.
hold on. Hold on. Otherwise, nobody at home can hear you.
So our agreement with the LLC is that we pay them $600 a year for the use, which is dirt cheap. And then for every outreach that we do, we can save $200 off of that, up to $400 savings. So a lot of times they'll do a fundraiser or something, and we'll come up and do a lecture, a star party, and that reduces our amount. Since COVID, I'm not sure that we've really exchanged any money with them. And I got to talk to Matt about that to make sure that's actually happening. But it is really dirt cheap for what they are giving us.
Well, the other thing, Ken, I was thinking for MAS speakers, what you're talking about, giving them a little stipend.
Yeah, so the stipend for an MAS speaker is $50. So before, we never paid our members to do daily lectures. Now we're giving them $50. And then if for outside speakers, it's up to $350, depending on who it is. But yeah. Yep.
And it includes lodging.
Yep. Includes lodging.
Okay. All right, great questions. Anybody else? Okay. All right, we are doing our little PSA announcement. We do have I don't know, did you want to come up now and talk about it? The astronomy astrophotography meeting?
Hi, everybody. As I've mentioned for the past couple of meetings, the August meeting, we're going to be featuring your pictures. Email me couple, 2 to 3 pictures that you've taken in the past couple of years. It could be something you've taken through a telescope and with your setup and all that stuff. Write me a good narrative around that and be prepared to talk through the meeting. And it could also be some pictures were taken with cell phones, and they're amazing ones. Just share those pictures with me, and that's what our August presentation is going to be about. And we have a surprise for those who participate and send pictures. And if you want to send me pictures, you can email my board member email. If you have my personal email, also feel free to email that one. Just make sure you're sending me a high definition picture. Also, I've gotten high def pictures using Slack. That's good. The one I don't recommend is the forum, because it would actually reduce the number of pixels and pixelate the image, and it wouldn't actually stand out nicely. As long as you can get me a high def picture with a narrative, that's all I'm looking for. Thank you.
And they can also send it to you on Slack too, right?
Yes,
The
so Slack,
the-
by board email or personal email.
Okay. All right, perfect. All right, thank you. Give it to Matt. Otherwise, I do feedback. And then we have the Virgo Venture, which we tried it last month, but there was nobody available. So this time we do have some prizes, and hopefully we have people here in house.
So good evening, everyone. My name is Jerry Jones. I happen to, one of the hats I wear is the co-observing chair. The other co is sitting over there ignoring me. There he is. He's waving at me. So this year we did, we actually, pardon? Oh, Chris Setness, who's continued to ignore me. That's okay. I guess I'm very ignorable. Oh, you're okay. All right. That works. That works. So this year we actually did had a Virgo Venture. Messier Marathon was scrubbed. We had a Virgo, and it was very well attended. We had what, 4,000 or 5,000 people there, something like that. I mean, it was, and then we had telescopes just kind of like that. It was amazing. It was amazing, and we had decent skies. Yeah, that's right. Choreographed. Everyone looking this way. Now everyone that right. No. But we had decent skies, and we actually had a few people who were foolish enough to do the list, and some people who were foolish enough to actually find some of them, which is really cool. And they turned it in, and they weren't board members. There's a lot of different things. You got to jump through a few hoops. That's why you didn't win, because you're a board member. Exactly right. Yep. So I have some prizes. And I have these really cheesy, totally cheesy certificates. I mean, about as cheesy as absolutely possible, but it's the thought that counts, right? Okay. So yeah, yeah, all right. One-handed clap. So Ryan and Macaulay Hansen, they came in together. They picked up 12, and we have a shirt for this guy. Congratulations. Here it is. No, you can't forget the cheesy diploma. No, I mean, I spent all of 30 seconds making that sucker, so you better take it. But what? Dairy-free cheese. Steve is not here. Steve Kaler is not here, I don't think. Mark Peterson is here. Mark Peterson, congratulations, found all 25. And he gets a mug that I forgot. And I also forgot to tell Merle to bring one. And then Dan Homdahl. Dan, are you here? I didn't think so. And Dan found all 25, and he gets a t-shirt as well. So the thing about the Virgo Venture, the mini Messier Marathon, and the Messier Marathon is that those are three that are organized and scheduled star parties. We have star parties at CGO and at LLCC all the time during the ELO. I'm sorry, no, and ELO as well. Yes, I was thinking of LLCC with the three of them, Virgo Venture, Messier Marathon, and the mini Messier Marathon, the MAS mini Messier Marathon, known as the 4M. And so those are ones that, because they're scheduled and they are called on or off depending upon the weather, it's pretty certain there's going to be other people there. Obviously, there are star parties at especially like at CGO that at any time you can go down there, but you may not. You may be the only one there. But this is one where you're pretty much guaranteed. And like I said, we had 5,000 people there last time, which was pretty awesome. So our next one is in the fall, the MAS Mini Messier Marathon, where you see almost as many Messier objects as you see in the spring. And I don't remember the date. I should have that off the top of my head, but I don't. But it's but the assistant, the co-chair, the co-observing chair is looking it up right now, and he will let you know. And beyond that, I will send you back to Tarina.
There we go. I turned myself off. That's okay. Thank you, Jerry. Appreciate that. So yay, round of applause for Jerry for doing that, and Chris. Just a side note for the eclipses that are getting a little bit closer. As of today, we have 101 days to the annular eclipse, which I think a few people are going to. I know, TikTok. And then we are under 300 days, the big eclipse in April. So hopefully everybody is starting to get their stuff ready and planned, and praying that nothing gets canceled, and hoping that the whole entire US is clear, not cloudy. So we can try. But I would like to actually have Mark come on so he can talk about our next little public service announcement.
I'm here.
All right, there you go. You're up.
Hey, good evening, everybody. I'm kind of pushing this this Globe at Night program. So this month, July 8th through the 17th, which if you are paying attention, that's surrounding days before and days after the new moon. And what the big deal is it's an international citizen science campaign. It's been going on for a couple of years. I believe that this is the second year. And specifically, Starry Skies North, who's the dark sky chapter for Minnesota, they are trying to get 500 observations in 2023 by anybody, anywhere, anytime you're out in the evening, or even early morning, during those dates to make an observation. Now, all of us could make an observation each one of those nights, providing it's clear, and report that. So if you go to, if you want to participate, go to Globe at Night, just Google it, it pops up. And what the cool thing about it is that you do not need to register. You do not have to be an adult, so children can do this. There's no data collected from you. The data that we're interested in, or the data that they're interested in, is how dark is the sky where you are. So if you live in Minneapolis, make an observation. If you're up at LLCC or CGO or ELO, or Metcalf Field during those dates, make an observation and report it. It's simple. You go to globeatnight.org. You go to you go to report, and a menu will pop up. And in that menu, it will give you 2 or 3 different constellations to look at, and you just record what you see. And the way it works really is if you're in a dark place, you're gonna see a lot of stars. So if you're looking at Hercules, you're gonna see a lot of stars in Hercules. If you're in the inner city of Minneapolis, You know, you're not going to see not so many. So you may see Vega and you may see Arcturus and you may see a couple others. Then that's what you report. And what's really cool is you report your location and the time that you made your observation. And what does the sky look like? They actually have different images that you can select, and you can decide which one looks like your sky that you're looking at. And you hit, and then when you're all done, you hit report and it's all done. Now, there is some additional information if you want to provide it about, you know, where were you taking this observation, and what was the sky like? Are there any, you know, are you standing in the middle of a target field making your observation during a baseball game? You know, so it's really kind of cool. And then those of us that own sky quality meters, there is also a place on that report form where you can just log on, report your location and your time and your sky quality meter reading and be done. And it's as simple as that. Trina, give me the next slide. Thank you. So Starry Skies North is adopting October as the Globe at Night month. They're also doing dark sky awareness presentations as many times as we want, or available. Whoever will invite us, you know, we're looking for places to do that. We've also chosen to show up at the MAS Star Party at ELO, and we're planning on talking with the leadership there to kind of take over the night as far as presentations are concerned, and provide a presentation and talk to the public about dark skies. That's, you know, so save that date. We're going to be there. There's probably about 20 members maybe that may show up from Starry Skies North, because, you know, we're scattered all over Minnesota, all the way from Moorhead to Duluth to Ely and farther south to Rochester and areas like that. So Starry Skies North, it pretty much covers the state pretty well. So you know, anybody may show up. So that is my little pledge, poke, help. We'd like to, you know, we're trying to get 500 readings this month. So maybe help us out, see how that goes. So thank you for your attention. Have a great night, everyone.
You too. Thank you, Mark. Appreciate that. Do you know what they're currently at for readings? I mean, is it 500 for each month or 500 for the year?
We're after 500 for the year. Last year, the whole, you know, so the Globe at Night is an international organization. Last year, they had 19,953 readings. This year, they're trying to get 200,000 readings. So they have big goals, and they're trying to use this data to make the public more aware of the fact that every 10 years we're losing almost the magnitude. You know, I mean, with the growth of I guess I didn't say that right, and I don't know if I have the right language in my head right now. But you know, we're losing dark sky so fast that it's actually faster now than it has ever been in the history of us humans. And the part that is fascinating to me is that it's one of those things that we can fix it, and we can fix it quickly, you know, because we just have to walk over to that switch and turn it off, and then it's dark. So that's where we're going. So thanks. Anything else?
I am good on my end. Anybody on chat have a question? All right, sounds good. All
right, good night.
We will, if anybody has any further questions, we'll make sure that you get in touch with Mark and get those questions answered. So
Thank you.
thank you. All right, at this time, I'm going to invite Jerry back up to do his little presentation for the Astronomical League Awards, if my screen would move that way.
Yeah, what are my chances?
I don't know,
What are my chances?
actually.
Thank you.
Well, good evening again. The other hat that I have the pleasure of wearing is the Astronomical League coordinator for the Minnesota Astronomical Society. And the major part of that task is coordinating the Observing Awards, which is the situation where all you guys send your logs to me, and then I steal your best ideas, and that's where I get all of these pins. So that's kind of how it works. So I really like this part of the job. That's part of the reason why my neck is heavy right now. But in all truth, we have so many new members that it seemed somehow appropriate to do just a little bit of a revamp and a remind of what these Observing Awards are. So the whole purpose, that's what's going to go on tonight. A bit of a history of the history of the observing programs and the Astronomical League itself. For those of you who don't know, the Astronomical League is our parent organization, and there are over 300 groups like us over the course of in the country. But this was new information. I wasn't aware of this number. 23,000 members. That's a lot. That's a lot of members. It's pretty cool. 23,000 members. Its purpose is to promote the science of astronomy in these three particular ways: to foster astronomical education, which they do in many different ways, including the Reflector magazine, including the observing projects, including other things that they do, assisting communication among amateurs, among amateur societies, and among professionals, which again, that they do in various ways, including the Reflector, which we all get. And the third one being providing incentives for astronomical observation, which is really where the observing projects fit in place. So what the Astronomical League does and has done for many, many years is to provide projects for us to do, which includes and incorporates learning and going out and using our telescopes. So that's that's the part of it that I am mostly involved in. But a little bit of a history before we get to there. The whole Astronomical League started in 1935 with a failed attempt by the Milwaukee Astronomical Society with a bunch of other Midwestern clubs, and their title was the American Amateur Astronomy Society. Sadly enough, it was right at the end of the Great Depression. It was expensive, so it got dropped. A few years later, it was tried again, although this was on the Eastern Seaboard. And again, it was attempted in 1941. It was called the Amateur Astronomers League of America. What great names, huh? Kind of makes you feel like some sort of a superhero, right? Exactly. But unfortunately, World War II came along, and it was kind of, as so many things in our society, it was put to rest for a while. However, it came back 1946, and it was called, again, the Amateur Astronomers League, and it was shortened at that point in time to the Astronomical League, which we now have. First convention was 1947, Philadelphia Franklin Institute. But here's some really interesting stuff that I wasn't aware of. The first president was Harlow Shapley. Now, some of us will know who Harlow Shapley is. Fairly famous astronomer. He was the guy who was involved in the great debate in the 1920s with, who's the other guy? Anybody know? Heber Curtis. Heber Curtis. Curtis was on the side, and the question, of course, was, are all of those things that we see that look like these flurry of stars, are they within our Milky Way, or are they outside of the Milky Way? They were called island universes at the time. They weren't certain what they were. And during that debate, Shapley took the side that it was in the Milky Way. Curtis took the side that it wasn't. Obviously, we know the answer. And Shapley really kind of took his lumps very well. This was out when he was at Lick, that he made this. An interesting thing is that he took the train from California to Washington, and Curtis was on the train with him. Kind of an interesting little thing. You wonder kind of what they talked about if that was the case. So there has been a connection, and of course, Shapley did a great job. He landed on his feet. He wound up with the Harvard Observatory job, which was a huge job, very, very important worldwide job at the time. So we don't need to be too concerned about him. But he did have a serious interest in amateur astronomers. He saw that there was something about amateur astronomers that was necessary for the development of the professional organization. So hence the reason why he was very involved in the beginning of the Astronomical League and became the first president. Now, the third president is also a name some of you will recognize. Anybody recognize it? Charles Federer, first editor of Sky and Telescope. Hence the reason why Astronomical League and Sky and Telescope also have a connection. That's kind of cool. In 1958, they had 7,000 members, 110 societies. We, as the Twin Cities Astronomers Club, didn't really happen until 1972, so we weren't part of this. And in 1966, the first observing program was approved, and that was called the Messier Observe, which was obviously what's turned now into the Messier Project. In 2001, and this is where things get interesting, even more interesting, a committee was formed because the Astronomical League recognized that they had all of these observing projects, but they needed to put some sort of cohesion within all of them. So there was a committee that was set up, and it took them quite a number of years, but they did what I think is a pretty bang up job in pulling together. So before the committee, there was just one goal for all of these projects to observe, and that was the master observer. If you did the 5 core and you did 5 additional, you wound up being a master observer. But it was after 2015 that they decided to take that and turn that into a much larger curriculum. So now there are 5 levels. There is the observer level, the master observer, the advanced observer, the master observer silver, master observer gold, master observer platinum. And then there was also an additional a binocular master as well as an imaging master award. So what their point there was for those of us who, you know, are somewhat goal oriented and like to have heavy things on our lanyards, they spread it out a little bit more and gave a few more goodies and a few more former directions, which is kind of cool. So this is how we as an organization stand. We have 6 members who have the Observer Award. We have 11 Master Observers, which is one of the largest numbers in the country. It may be the largest, not one of the largest, which is, these awards are, there's a lot of work involved in them, hence the reason. We have 3 Advanced Observers. We have 3 Silver Observers. We have 1 Gold Observer. And we have 2 binocular, we don't have any Platinums. Some of these were fairly new, of course, obviously since 2015, and it takes a number of years to get these things. And we have no imaging masters. Now, I will grant you that it's fairly early, fairly new. It's only been a few years, but I would think that we could just have a gob. If any of you imagers out there would get your act together and start. Just kidding. Currently, the Astronomical League has 86 different programs, 86 different observing programs. They have given out 16,075 certifications, of which 483 went to us. Okay. As of 2023, the sequence of the awards have been redesigned. And this is, and I'm really pleased that they did this, because when you looked at what was considered beginning, intermediate, and advanced, in a lot of ways, it didn't make a lot of sense. There were some things that were really hard, in my opinion, that wound up being in the beginner column. And there were some that seemed pretty darn easy that were in the intermediate, the advanced. And you kind of wonder what the heck's going on. So they did a great job. The curriculum, the coordinators, the committee did a great job, in my opinion. So there are 28 beginners, and the whole point of them is to focus on learning, developing some certain particular observing skills, and gaining particular things having to do with those observing skills. Like, for example, double stars as a beginner. In double stars, you'll learn about position angles. You'll learn about angle of separation. Those are really important concepts if you're going to go on and do other things, that sort of stuff. The intermediate, there are 30. And that is primarily where a lot of the just get out there under the skies using your telescope and doing some observations. And then there are 28 advanced. There's a greater emphasis on observing, but particularly using larger aperture and darker skies. So we just happen to find that to be true, that the farther along you go, just a little bit better gear. You're not going to be able to get by with a 4-inch in downtown Minneapolis and attempt to do some of these advanced ones. Just not going to work. So the beginner is a kind of a mixture of armchair and actual observing. Like, here's some examples. Alternate constellations. What a cool concept. We are so used to the 88 constellations of the IAU that we don't even think about the fact that there are so many other cultures. For millennia, human beings have looked up at the sky, looked at the stars, and made patterns out of them. And so here's an opportunity to look at other cultures and see what kind of patterns they created. How cool is that? But that's something that you just do with your naked eye. So it's, as you can see, there's an example of very much more of not just strict observing, but observing and learning something totally different. How the observing projects for the lunar worked out. Lunar one is very easy, very straightforward. You find 100 objects. Some of them are small, some of them are big. But then within the beginner, there's also lunar evolution, which is specifically about the geology of the moon and how it's changed over the course of billions of years, and which particular artifacts are in this particular epoch or this particular epoch. So there's a lot of armchair work, but then there's also some observing and some sketching. By the way, sketching is considered a beginner project now, which it wasn't before. And that makes sense because many of the objects on that list are fairly easy to find, but it's the development of the learning process of how to sketch is the key there. And sketching just makes you a better observer. It just simply, it doesn't matter how good or how bad you are. The fact of having to put a piece of a pencil to a piece of paper while you're looking at the eyepiece forces you to observe better and see more things that you would not have seen before. So that's kind of cool. And here's some others. As I'd mentioned, double star mentioned sketching, learning how to look at the sun, learning the equipment, learning what the different aspects of sunspots and all that kind of stuff. So you can see where these are just a lot of learning basic concepts and skills in astronomy. Intermediate, based upon the skills that were initiated. Advanced, binocular double star, that makes sense. Asterisms, oh my word. Trying to figure out who in their right mind took that grouping of stars and turned it into a teapot. And that doesn't look like a teapot at all, but you got to find it. I mean, those kind of things, but that requires a different way of utilizing skills that you developed in the beginners. Messier, I found this great. The Messier list is not necessarily easy, even though it's the one that's always suggested first. There are some really hard things to find in the Messier list, and you have to find them with star hopping. Well, you learn star hopping in the beginners, like, for example, the lunar one is great star hopping practice. And you're looking at me like you're out of your mind. Crater hopping. You figure out, oh, there's that crater. Oh, I have to go to here and then to here. Oh, there's that crater. That's the one I'm looking for. It's the same concept. The only difference is using stars as opposed to craters. So they've moved that into the intermediate, which I think is great. And the Bennett list is the southern skies Messier list. Hydrogen alpha, solar hydrogen alpha. It builds upon the sunspotters. And clusters, open and globular clusters. The advanced are clearly more advanced. The ARP galaxies groups and clusters. In order to look for galaxies and then be able to determine the morphology of the galaxies, it's going to require darker skies and bigger aperture. It's just simply necessary. There's no way you can determine an SC and an SB unless you have a bigger telescope and darker skies. Dark nebula and bright nebula. Sometimes they're easy to find, sometimes they're not. There all depends on transparency. Yeah, all these kind of things. Herschel 400 and the Herschel 2. Herschel 400 can indeed be done with an 8-inch in skies not, a little farther away, but the Herschel 2 simply cannot. And then there are some niche-oriented groups like radio astronomy. Those of you who want to get into radio astronomy or spectroscopy or near-Earth objects. Okay, so there's really something for everyone. But the real value, in my opinion, is that the projects give us intent. How many times have we gone out with our tail? We want to go out into the dark skies because we know something really cool happens when you're under the dark skies, under the stars. It's something that's really cool. I mean, we look up and we just recognize that we are who we are, and there are things that are way bigger than us, and that's a good thing. So we get our telescope out and we think, okay, what am I going to do? Well, I can look at the same things I looked at last time. Well, that TV program I'm missing is starting to sound pretty good. This is an opportunity for us to have different goals. I'm going to go out and look at variable stars, or I'm going to look at globular clusters, or I'm going to look specifically at the moon for specific reasons. I'm going to find these 5 or 6 things that I can only find, by the way, on the 7th day because of the way the angle of the sun operates. I can't see them any other time. Only certain times you can find Rupus recta. It all depends upon the shadow of the sun. Also, the value of learning specific skills, which is really cool, both observing and knowledge. You gain some information as you're out there looking at stuff. It gets you looking at things you've never looked at before. The multiple star system project, which is a great project. It's really hard. I don't think I would have ever looked at a quintuple galaxy gravitationally bound star system if I hadn't been asked to find it. It's gorgeous. It's beautiful. It takes some work to separate some of the closer members, but wow, they're out there. And I would never have found that if I hadn't been asked to by that program. There is no requirement to follow the sequence. You can do whatever you want. And there's a lot more information on astroleague.org. The way this works is if you want to get the certification, which is way better than the cheesy stuff that I handed out tonight, and a pretty cool pin, you do the project, and most of them you would send your logs to me. I'll steal the great information that you did and send it off to the national coordinator. And it would be nice maybe someday to be able to go back to the times when you were forced to be here at the meeting so I could hand you the certification and you could talk a little bit about your project. That'd be pretty cool. So here is a list. This is an old list, but here's a list of most of the projects. So I'm just going to give you a second and look at that list. And you're going to find, chances are there's something that tweaks your interest. Comets. Even being a dark sky advocate. Earth orbiting satellites, galaxies, globular clusters, the moon, open clusters, outreach. If you do a lot of outreach, there's a project for that. Library telescope, which isn't on there. That's another one. So there's just tons of them. Stellar revolution, which is a really interesting one. It's not terribly hard, but it's really interesting. And with that, get out there and observe.
That's it.
Questions? Anybody have a question?
What's the latest one that you're working on?
What?
What's the latest one that you're working on?
Well, I have learned that the real key to this is to work on multiple ones because there's sometimes you can only see certain things, so I've got asteroids and binocular variables and telescopic variables and planetary nebula and dark nebula and bright nebula.
All at the same time.
Well, yeah,
So I think you had
sure, because like the dark and the
10.
bright nebula, I only do when I'm in a dark sky site, but I can do asteroids here in town. Because most asteroids are, well, I mean, some of the ones you can see are 10, 11 magnitude, And, so most of an 8-inch is going to, in a suburban area in Minneapolis, Twin City, you're going to be able to see an 11 mag star. So I do the projects of where I am, but I'm not going to do asteroids when I'm up at LLCC. That would be silly. I'll do planetary nebula or bright nebula. If I go to Oklahoma, to Okie, someplace like that, and the transparency is off the charts, dark nebula, because that's the only way you can see a dark nebula, if the transparency is pristine, or else they're gone. You can't see them. One of the better observers in the club, Mr. Srinivasan. Great question. Even better question. Can you please repeat that? So Suresh just asked, what are some of the projects other people are working on? Lunar 2, a hard project because it is all dependent upon shadow, which is wonderful. Yeah, right. Yeah. I mean, there are some things you can only see at particular times. How awesome is that? Because it's all about the shadow. But there are a couple of really great books about Lunar 2 that really make it easier.
Yeah. I've got the carbon stars and
Stars
and Herschel 400.
Carbon stars. How cool. Red stars that really kind of look red sometimes, but they're not red giants.
No.
Which is another really cool thing, that they're not red giants, but they're still red. Why are they red?
But not all of them are red.
What?
Not all of them are red.
Not all of them are visibly red.
Right.
And there's a project.
You learn different things.
There's a project that's helpful to not be completely dark adapted.
Yep.
Because you can see, you need your color cones to see red.
So is that a good one to use when the full moon is out too?
Yeah, maybe. Same way, you make PDFs of your sketches and send them in. Yeah.
Yeah. So Steve's question was, if they're sketching, how do you send the logs to you?
Yep.
And same way you can scan them. You can.
Right.
I think I took pictures and
Right.
sent you some of those.
And remember, it's always helpful to throw some sort of a spreadsheet that gives an idea of the overall concept of what you've done, rather than just throwing a bunch of disorganized PDFs. It just takes forever for me to go through them.
And you're
Any other questions?
And you're a busy man.
Well, no, not as busy as some of you.
Any
Any other questions?
I think there's a question on here.
I am 5 minutes over.
And Anton says galaxy groups and clusters he's working on.
Galaxy groups of clusters. Man, that is a tough project. That's a toughie, but he has an 18-inch teeter, so he's okay.
He's already done spectroscopy.
What is it, what is it, Anton, a 3.8 focal length?
3.6.
3.6, even better. With a parafocal in there, right?
So the parafocal makes it about a 4.2.
4.2, oh, loser. All right, any others? Great, thank you.
Thank you. So if you have questions, we'll get a hold of Jerry or we'll figure out how to help you out. So but take a look, and they're not hard, and you do get cool pins. They don't always have to be as many, even though I think you're on lanyard number 2.
Well,
there's a few in the back.
I get pain in my neck.
Tougher. All right. Well, I'll just keep this real quick for the rest of it. So I just want to thank everybody who does volunteer. So there are volunteer opportunities for any of the new members that are out there or watching this later on. Thanking Jerry Jones for being the observing chair, Ken for LLCC, Lila for our public outreach coordinator, and Valtz for all of his website doodads that he works on. And of course, as you're doing any projects, keep in mind that you can write about it too and submit an article to the Gemini that Father Brown will post. Deadline is Monday, July 10th. And then it will be published in August. And then, of course, in a couple months, we'll have the next deadline because it's published 4 times a year. Yay. Yeah, but that's tonight. But I think it has until July 10th to be. Oh, 6 times. Sorry. Yeah, you're right. Sorry. My bad. 6 times. Then, of course, if you need something a little bit more immediate, if there's something going on, send an email to the secretary and he will get it posted in our little happenings newsletter. And then I am looking for a volunteer for September for Better Know a Constellation or Better Know Volunteer or any kind of program that you want to talk about to share with the club. We always love having members come up here and teach us a few things. So thank you. And then our next meeting is going to be on August 3rd here back at the Educational Center, doing the Astronomical Society's Astrophotographies program. What? Andetu Teta Educational Center. I'm still not very fluent in that, so it takes me a little while to put it together. I've got the link right here in my notes, how to say it. And then we are going to take a little bit to get our speaker, for tonight, which is Professor Ali Sulaiman. Thank you. And I'm going to have Ahmed come up and introduce him while we are switching things over. So just a moment. Do you want the headset?
Thank you, Trina, and thank you, Professor Ali, for coming out. As usual, with a lot of speakers that I book, I usually look them up and look up the research and see, okay, this is something that would interest the club, and then I reach out to him or her as a speaker. And in this case, he is a professor at the University of Minnesota. Reached out to him. I didn't actually know his history a lot. I was more interested in his research, but then came a couple of things that were interesting in the background. The first one, he is actually Lebanese, just like me, which didn't know until actually today when I actually met him in person. And then the second thing was a couple months later when we had Professor Spangler come and join us, and he talked about Venus, and he said, hey, if you're interested in somebody who's really good talking about outer planetary exploration, you need to book Dr. Ali Sulaiman. Interestingly enough, at that point, I already had him booked, and it was like, okay, I already have him booked. And we talked about that briefly in that meeting. So we're finally getting to hear him, and I'm excited about his talk. So let's welcome our speaker. It looks like the presentation is ready.
Thank you, Ahmed. So I spent a couple of years at the University of Iowa, and maybe there were 3 things that were lots of fun there. One of them was Professor Spangler. So I hope you enjoyed his talk. He's a real treat. Today I will give an overview of the outer planets, specifically exploration of the outer planets. So I'll highlight some key discoveries by present missions and also introduced some future missions. Some of them are off the ground and some are still on the drawing board. Really, this is an enormously rich topic. So I will specifically focus this. Essentially, we'll be looking at the outer planets through the prism of magnetic fields and plasmas. Okay, so what we have here is, is anyone familiar with this spacecraft? This is the Juno spacecraft to scale. No, that's a joke. So this is this is the Juno spacecraft, and actually it's overlaid on a James Webb Space Telescope image of Jupiter's system. And I say system because you can see the faint diffuse ring there, and then to the left, that is one of Jupiter's innermost moons, Amalthea, and then to the right, you can't see Io, which is the innermost Galilean moon, but you can see a diffuse kind of extension of the Io torus. So Io really will be a key player here. Now, Juno is the second orbiter of Jupiter. The first was Galileo from the 90s through the early 2000s, but Juno is the first polar explorer. That's actually a very difficult thing to do, to get spacecraft into polar orbit. But that was successfully achieved, and it's giving us the first views of Jupiter's poles. One of the most spectacular displays of Jupiter's poles are the auroras, and actually you can see that there's some nice altitudinal extent to the aurora and the ultraviolet. This is called an auroral curtain. That's just a band of light that encircles Jupiter's poles, much like Earth's aurora, of course. Okay, so I thought was it okay.
So done. Maybe. Not presenting right. Sorry. There we go.
Okay.
There's the right slide. Should be that one. There.
Okay, great. So let's see if I could. Okay. So I was. Yeah, I'm going to see if I can just pull up a pointer here. Or does anyone have a laser pointer I could borrow? I think I noticed one earlier. Okay. Yeah. Okay, yeah, that'd be very handy. Thank you.
I don't have.
Okay. Great. Okay. Yeah. Or it's I. Oh, either way.
Oh, hello. Yeah, that's good. Go put it there.
Great. Okay. Thank you. That's great. Okay. So the sort of stars of outer solar system exploration were the Voyager spacecraft. Of course, it was Pioneer as well, but Voyager in particular, because it undertook the so-called Grand Tour, which is actually a very rare event in terms of planetary alignment. But the timing was right in the late 70s, and it launched the two of them such that they could conduct a tour whereby they go past all the outer planets. Now, Voyager 1 actually went on sort of a suicide maneuver when Titan was discovered. And so that sort of went off the ecliptic. But Voyager 2 actually continued all the way through out to the edge of the solar system. Until 2013, so on the BBC, as well as I'm sure other news outlets, there was a headline saying that Voyager probe left the solar system. So this announcement came on one day. And so it sort of asks, maybe begs the question, you know, what is the edge of the solar system here? And actually, there are many definitions of what the edge of the solar system is. You might think as far as maybe the Oort cloud. But in the context of plasmas of magnetic fields, and the reason why I'm introducing this is kind of just to put into context where the outer planets are in the so-called heliosphere. So this boundary actually that the Voyager spacecraft crossed is the heliopause, and that is the outermost boundary, or if you like, the outermost magnetic field line that is connected to the sun. Okay, so the sun sits where it is in the solar system, but actually its magnetic field line is essentially a huge inflated bubble that envelops the entire solar system and far beyond. And this heliopause, this boundary, essentially confined by the ram pressure from the interstellar wind. Okay, so the sun itself has a wind that's blowing off. So that's not electromagnetic radiation, but it's just, you can think about it as the extension of the sun's corona, composed of plasma. It's blowing off continuously at about 400 kilometers per second. And that goes all the way up to the heliopause, where the dynamic pressure of that wind is balanced by the dynamic pressure of just wind that's coming from other stars. Okay, so here's where it crossed, and the reason why it has somewhat of a bullet shape is because there's a relative velocity. So the solar system is moving at a certain direction with respect to the Milky Way galaxy or interstellar space. Okay, so then comes the question: is space empty? And as I hinted, space is actually not empty, and it is filled with a certain state of matter. That although it is very rare to occur naturally on Earth, of course, at Earth we have solid, liquid, and gas. But once you go out into space, the fourth state of matter is plasma. And actually, plasma occupies, does anyone want to take a guess how much of the visible universe is composed of plasma? Yeah, about like 99.9% or so. Yes, exactly. So even though it's rare on Earth, it is pretty much almost the entire visible universe is composed of plasma. Of course, the invisible universe is dark energy, dark matter, so things that we can't measure directly. Okay, so just some fundamentals of plasma. So if you think about a gas, or actually if you think about a solid, maybe if I go back, you can see that the distance between two atoms or molecules will increase as it changes phase. So as you go into liquid and as you go into gas, that distance increases. So it becomes more and more tenuous and less dense. And that's the same with plasma, but not only the sort of interatomic distance or the intermolecular distance, but actually the distance between subatomic particles. So those break free from one another. So here's what a gas looks like. You have these subatomic particles are bound together through the electrostatic force between the nucleus and the electrons. But actually in plasmas, they move kind of freely from one another. I don't want to say independent of one another because there's an electrostatic force between the protons and the electrons as they move. But it's essentially a soup of protons and electrons. And this is what pervades the heliosphere and pretty much everywhere between stars in our universe. Okay, so I've found this nice image of our visible universe. And this is sort of on a logarithmic scale. You have here the Earth, and you have our planets. You have the moon, comets, Jupiter, Saturn, sort of asteroids, and all that. And that's obviously less than 0.001% of the visible universe. And everything else at monstrous scales are what's composed of plasma. So like you said, anything that glows. Okay, so what's plasma actually composed of? So it depends where you look for it. So if this is just in the interplanetary medium, the solar wind is composed of helium ions, mostly of protons or hydrogen ions, as well as a minority of helium ions. Earth's magnetosphere. So here's the other term that I'll be touching on a number of times during this talk, is the magnetosphere, which is essentially the bubble around a planet, or in this case, Earth, that's carved out by its magnetic field. Okay, so the Earth's magnetic field, essentially, it's the near space environment that's influenced by the Earth. That extends out to about 15 times the Earth's radius. So it's pretty large. And that magnetic pressure is stood off by the dynamic pressure of the solar wind. So it's being continuously impinged upon by the solar wind. Now, inside this bubble, you also have plasma, and that plasma originates from Earth's upper atmosphere. So through typically Jeans escape is one way that you get some of the ionospheric material that escapes the Earth. And those are mostly in the form of protons and oxygen. Then we will move to Jupiter's magnetosphere. And because of Io, they're composed mainly of sulfur ions and oxygen ions. So there's a bit of a typo here. And then roughly equal numbers of electrons. And that's because this is one fundamental property of a plasma. Over any given volume, it has to be quasi-neutral. Okay. Now, to get a feel of the density, so air contains 20 and however many zeros that comes after that. I mean, even though air feels like almost you can't really feel the pressure that's on you, you can easily move your hand around and almost not feel that there's something in the way. But actually, that's how much there is in there. So I started putting these points in that box this morning, and I had to stop somewhere. But for comparison, a plasma just has 1 per cubic centimeter. Okay, so space plasma is extremely, extremely tenuous. Now, it's extremely tenuous to the point that it behaves as a fluid because, we call it a solar wind. But actually, what kind of makes a fluid be called a fluid is that it exhibits some collective behavior. So you can prescribe a fluid by its temperature, by its pressure, by its density. And what gives it sort of that average collective behavior like is essentially the collisions. So air molecules are in continuous collisions with one another. So they sort of spread out, or they smear out any energy that's being input into that fluid. Now, with space plasmas, it's effectively collisionless. Actually, on average, for one plasma in the solar wind, one plasma particle to collide with another, the mean free path is 1 astronomical unit. So that's how far it needs to travel before it collides with another particle. Yet it's still a fluid. It still behaves as a fluid. Okay, and so can anyone guess why is it a fluid? Why is it not just individual isolated pellets in space? There's no collisions, so they never run into each other, but yet they still exhibit some kind of collective behavior. So why would that be? Yeah. Not quite, Brownian motion has collisions, but these don't see each other. Yeah. Sorry? Yes, exactly. So it's electromagnetic fields. So they can actually communicate with one another over very long range electric and magnetic fields. So they do exhibit a fluid-like behavior. Okay. So the first property, as I mentioned, is that space plasmas are quasi-neutral. The reason being just because if you separate them from one another, an electric field will be established to bring them back together. And then also, as you mentioned, there are electromagnetic fields. There's another property which is called the frozen-in condition. And I'll come into the implications of that when I talk about the auroras. But essentially, on sort of large scales, if you had a blob of plasma, so let's say this is a blob of plasma that's emanating from this planet or the sun rather. Now, this arbitrary volume has an arbitrary number of magnetic field lines that's threading that blob of plasma. Now, as the plasma moves away from the sun, it cools, it expands. You'll have the same number of magnetic field lines that are threading that same blob of plasma. So in a way, it's retaining its identity. Okay, so this is called the frozen-in theorem, the frozen condition, and I'll talk a little bit more about just by applying the frozen condition, what discoveries can be made in the solar system. Okay, so to give a graphical feel, if we take the whole journey from the sun towards the Earth, we essentially have the solar wind, 400 kilometers per second, continuously blowing away from the sun. Embedded in that solar wind is the sun's magnetic field. We call that the interplanetary magnetic field. So that's being dragged away from the sun. As it moves away, it cools, it expands, and then it impinges on the Earth's magnetosphere. Now, the Earth's magnetosphere acts as a shield because these two plasmas can't mix because of the frozen condition. The plasmas are locked into the magnetic field of the sun, and the Earth's plasmas are locked to the magnetic field of the Earth. So the Earth's magnetic field provides a barrier to the solar wind, and in a sense, this gives us protection from these highly energetic particles. Now, under certain conditions, obviously the sun's magnetic field has a certain orientation to it, but when the orientation is right, you can get a process kicked in called magnetic reconnection, and that's really how the auroras are generated. So this is simply what the reconnection process is. If you have the sun's magnetic field on one side, you have the Earth's magnetic field on the other side, so that's the Earth's magnetopoles. If they're anti-parallel, well, this is an ideal case. They don't necessarily have to be anti-parallel. But if you look at this example, you can have these field lines essentially reconnecting. So these two field lines that are closest to one another, close to the interface here, they essentially get snipped, and then they reconnect and they move leftward and rightward. Okay. Now, this is a process by which you have magnetic energy. So there's stored energy in the field lines. They get converted into kinetic energy. Okay. Now, the plasmas are, of course, locked into these field lines. They're frozen in. So once these magnetic field lines snap away, the plasma shoots off away with them. So you create jets. So here's an image of the sun. Of course, in detail, there's a lot more structure associated with it. We were talking about the eclipse. Actually, the eclipse is an excellent opportunity to view the solar corona and the solar wind and the magnetic field lines that are emanating from it. So of course, the field lines are invisible, but what we're looking at is the plasma. But since the plasma is locked into the field lines, then this is an indirect way of essentially looking at the topology of the magnetic field lines. Certain points of the sun, you get these coronal loops. Again, what we're seeing is the plasma, but the plasma follows the field line. So we have this topology. But you can see if the field goes up here and then down here, if these two foot points are close enough together, you can get magnetic reconnection occur. And this is an explosive event. So that leads to the explosive release of plasma away from the sun. This is in addition to the solar wind, which is always happening. Solar wind is always happening because outer space is almost a vacuum. The pressure is very low, and the sun is a ball of high pressure. So that pressure gradient strips away material from the sun continuously. But in addition to that, you get sort of transient explosive events in the form of coronal mass ejection, and that kind of leads to a much more bigger blow to the Earth's magnetosphere. Now, once that arrives, you get essentially a point where the field lines are anti-parallel and reconnection occurs. Now, when reconnection occurs, the field lines of the Earth's magnetosphere open up. And when they open up, they go along for the ride with the solar wind to the night side. And then they reconnect again in the tail side. And so this portion here shoots off to the right into eternity. This is called a plasmoid. And then this point here shift towards the Earth, and you have plasmas are essentially accelerated along field lines. And just given the topology of a dipole, they get funneled into the polar regions of the Earth, and they precipitate into the atmosphere and lead to emission lines. So that's how the auroras are generated at Earth. Now, Earth's aurora is an example of an externally driven aurora. In other words, it's driven by the solar wind. So it's whatever's going on in the solar wind, the conditions in the solar wind are what essentially control the aurora. So sometimes we can get a heads up by looking at what the interplanetary magnetic field is at Lagrangian 0.1, and we can get some form of prediction for the Earth's aurora. Now, this is a very different story in the outer planets. Okay, so looking at the magnetosphere of the outer planets, well, we have an inner planet here. We have Mercury. It's a very small magnetosphere, and then you can see to scale, the entire Mercury system can fit planet Earth. And then here's Earth's magnetosphere. As I mentioned, it's about 15 Earth radii. And that essentially fits into Saturn. And then here's Saturn in the system, which essentially fits into Jupiter. So Jupiter has the most massive magnetosphere. It's the largest structure in the solar system. It's actually larger than our sun. And if it were visible to the naked eye, it would be larger than the sun. I think maybe 1.5 degrees or so. Now, to go back to all these scales, I mentioned it's 15 Earth radii, which is the sort of day-side extent of the bow shot of the magnetosphere. At Jupiter, it goes up to 100 Jupiter radii. One Jupiter radius is over 74,000 kilometers. Okay, so about 100 Jupiter radii. So can anyone guess the night side as it sort of extends away from the planet? How far? So if it's 100 Jupiter radii on the day side, can you throw a number? Yeah. Great. Okay, you got it. Absolutely. I don't know what that number is, but it goes past Saturn. Yeah. So that's how absolutely enormous Jupiter's magnetosphere is. Yeah. Great. You know, you're the first person who knew this when I asked this question. Yeah. Yeah, it was measured. Yes. Right, it was measured. Yeah. There's a magnetometer on I think it was on Cassini, and it measured a certain topology in the magnetic field that could only be explained by Jupiter's magnetotail. Yeah, because of the alignment. Yeah. Okay, so we're talking about a really large structure in the solar system. Okay, so a bit about the missions. Here's the Cassini mission. So to scale, so this is a human. It's about the size of a double-decker bus. Cassini launched in 1997. And it ceased operation in 2017. So it actually crashed into Saturn's atmosphere and burned up. So this was a joint US and European effort. The US built the spacecraft, and the Europeans built the probe. So this is called the Huygens probe. So after the Dutch astronomer Christian Huygens. Cassini is named after an Italian astronomer. And I believe he discovered the rings. I may be wrong. Okay, yeah. Right, so this probe was actually deployed not onto Saturn, but onto Titan. And that's why I mentioned that sort of suicide mission by Voyager 1 when it looked at Titan and realized it was interesting, and it sort of broke off from its grand tour. And that's because in Titan, and I'll show an image, had a very thick haze around it. And so it's an interesting place to drop a probe because it has a very thick atmosphere, actually 1.6 times, I think, the atmospheric density of the Earth. So you can easily glide on Titan. And on the right here is Juno. Juno is still ongoing, launched in 2011, arrived in 2016, Jupiter, still healthy, still somehow enduring the harsh radiation environments of Jupiter's radiation belt. But so far, so good. And Jupiter's as far as you can go with solar panels. You need enormous solar panels to intercept a lot of solar energy from the sun. Saturn's too far, so Cassini was run on thermonuclear energy. So a bit about the payloads. There was a whole suite of instruments. So there were cameras. There was a visible camera, infrared camera, ultraviolet camera. Those were suited to look at the auroras of Saturn. But then there were also in situ instruments that were making local measurements of the plasmas. So you had a mass spectrometer. You had an electron spectrometer, an ion spectrometer, and a magnetometer, which measured the magnetic field strength and direction, as well as a radio and plasma wave instrument, which measures fluctuations in electric and magnetic field. So essentially, this didn't go to Saturn, but it went to Saturn's system. It went to look at the planet, the rings, the moons, but also the magnetosphere of the planet and how they all interact with one another. It's really a fascinating orchestra. They're really not independent things that are just doing their own thing, orbiting around the planet. They really all are in continuous interaction with one another. So here's Saturn's launch in 1997. And then this is the cruise that it took to Saturn. And now without a planet missions, we don't just launch them and they go straight to the planet. They have to conduct a series of gravity assist. And essentially they go into the inner heliosphere. They fly by Venus, sometimes multiple times. I think I've lost count of Cassini, but it goes by Venus maybe twice, goes by Earth. This is like a few years later after launch. It sort of comes back to Earth, does a flyby, then keeps going around the sun, and then eventually goes off towards Jupiter. And essentially this flyby it's an exchange of momentum between the two bodies. So Jupiter gives Cassini a kick, and so it can go very, very fast. And due to conservation of momentum, Jupiter also slows down, but not something that we have to worry about. It's a very, 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 very tiny, immeasurable amount. Now, you can do this many times. I mean, it saves fuel. You know, we don't really have a rocket that's big enough. You know, actually, taking this indirect route gets you there faster than if you were just to sail away to the planet because of this extra boost you get. You know, we don't have rockets that are just big enough to give you that boost. But of course, you don't want to go too fast, even though you get there in a very short period of time, because once you get to a planet, you need thrusters to slow you down. So you still need to burn fuel. So it's an optimization problem. Okay, so here's Saturn's system. We have the famous rings, and we have a number of these moons. Saturn has way, way, way too many moons, but these are some of the famous ones. Yes, same as Jupiter as well. And then the main rings here essentially are composed of ice and dust. Actually, they vary from the size of maybe little dust grains that are invisible to the naked eye and up to the size of boulders as well. So really, Cassini did it was a very daring mission, actually. Towards the end of the mission, it took an orbit such that it went in between the inner edge of the D ring and the topside ionosphere. So it was really, really, really remarkable, and essentially was taking lots of images of the rings, doing some gravity experiment, making measurements of the magnetic field lines connected to the rings, and so on and so forth. Now, one really interesting thing about Saturn is you can see that there's a very extended E ring, and that's a very diffuse ring. And that actually has an interesting origin, which I will talk about in a moment. And some of you are probably aware of the star of the moons here. Okay, so here's what Saturn looks like in the infrared. Sorry, this is in the ultraviolet. And you can see that there's an aurora, not unlike Earth's aurora. So even though it looks broadly similar in morphology, the way the auroras are generated are completely different. So I mentioned about the Earth, how the solar wind is the driver. The solar wind plays very little role in the outer solar system. And I'll talk about that in a moment. One thing about these outer planets essentially is that they generate radio emissions, and those actually come, that's also a kind of auroral process. So for example, if you have antennas out in your yard with enough sensitivity, you can pick up radio emissions coming from Jupiter. Okay, so they're called decametric radiation. And this is how we knew Jupiter had a magnetic field. This was back in the 60s. Long before a spacecraft got anywhere close to Jupiter and had a magnetometer measuring its magnetic field. It's because we could measure radio waves, and for radio waves to be generated, you need a magnetic field to do that. And now there's a very big sort of hunt for radio waves from exoplanets, because if we can measure those, then we can infer that they have a magnetic field. So why do we care about them having a magnetic field? Well, it ticks a box for habitability. Okay, so if we didn't have a magnetic field on Earth, then we wouldn't be able to survive the harsh cosmic rays and the radiation that's coming in from the solar wind. Okay, so falls into the habitability question. So another topic that I'll touch on a bit. Now, actually at Saturn, the radio waves were a little bit weird. So we also rely on radio waves actually to know what the rotation rate of the planet is. So that's how we knew the rotation rate of Jupiter. It's that you see it kind of like a lighthouse. It has a periodicity associated with it. And from that, they were able to infer what the rotation rate of Jupiter is. And that's kind of the way of doing it for the outer planets, for gaseous planets, because, they don't have a sort of Greenwich Observatory there that you can sort of time how long it takes for it to come back. And, the way the prime meridian is also defined is a bit arbitrary as well. Now, the problem with Saturn is that it's the only planet in the solar system, and this is very rare in the context of planets, but its magnetic dipole axis is perfectly aligned with its spin axis. Okay, so there's no tilt. Okay, so of course, on Earth, we know that there's a tilt. You have to update your maps every couple of years because the field is changing. And that's the same with Jupiter. But at Saturn, it's perfectly aligned. And for reasons I won't go into because I'm not an expert on dynamo action, but this apparently really, really challenges dynamo theory. So in order to generate a magnetic field, you need some kind of tilt. But Saturn doesn't have that tilt, and it's just causing a lot of confusion. Now one would think, okay, so there's no tilt. Let's see how we can measure the radio waves. So when it was first measured, this was by an instrument built at the University of Iowa, they actually found that the radio emissions that were coming up from the northern hemisphere were different from the radio emissions that were coming down from the southern hemisphere. Okay, so the periodicities were very different between the two. And that had a seasonal change. So actually during, let's see, is this maybe summer, I think? Yeah. So they sort of converge during equinox, the periodicity between the north and the south, and then they reverse as well. So this is a really big problem for timekeeping, you know, if you're at Saturn. So if you're in the southern hemisphere and you want to book an appointment in the northern hemisphere, then the length of a day in terms of the radio periodicity, you know, would be very different. So still, this remains an outstanding problem as to how do you have this differential rotation between the north and the south that has some seasonal dependence. Okay, so here's an image of Titan in all its glory, and you can see that there's a very nice, beautiful haze around it. This is due to chemicals called tholins. So Carl Sagan took a huge interest in Titan. Actually, was a really big force behind making the case for Cassini and dropping a probe on Titan. And indeed, in 2005, I think, and this is an artist impression, this was Titan, sorry, this was Huygens that was landing onto Titan. And I do have a movie here, which probably at great risk.
We'll see.
Okay.
See if I can.
This is just video, yeah. There are a few with audio, but actually there are a number of movies, I should say. Let's see. And yeah, Huygens descent, yeah. Okay. Oh, great. Okay. Yeah, sorry about the resolution. But here's Cassini.
Sorry.
No worries. Yep. Okay. And here's Huygens was deployed. And you can see the density of Titan's atmosphere. It's very, very thick. So you get a lot of heating, huge amount of drag force acting on the probe, and then you have a parachute. And another one.
Did they have a good idea of the density of the atmosphere?
Yes, they did. Yeah, yeah.
Not what you guess.
Yeah, so one way they can do it is through radio occultations. So they essentially fire radio waves towards the Earth, but have it pierce through the ionosphere. And then from those patterns, yeah, exactly. Yeah. Okay. So move on. Yeah, I'll move on to the next video. Okay. Yeah. Oh, okay. Okay. So the first video I showed you was Hollywood. This is real. Okay. Okay, will do. Thank you. Yeah. Okay, so I'll just maybe go a little bit ahead. Okay, no, this isn't real, but this is beginning to get real. So these are actually images of Titan that was taken by the Huygens probe. And you can see the landscape. So what's really fascinating about Titan is that it's very dynamic, and much like how we have the water cycle on Earth, at Titan, it's a methane cycle. So you have methane clouds, methane rain, methane rivers, lakes, you have beaches, and lots of geological features there. Okay, so I'll just forward this and
Anything there's something like soil or is it just ice? Mountains of ice?
yeah, ice, ice mostly, yeah. And then it's still not determined whether there's an ocean beneath the surface as well. So and I'll come into that in a moment as well. Okay, so this is where it landed. And then there's actually a mission called Dragonfly, which is kind of like a drone, which will be hopping about in Titan in maybe 10 years or so. So very, very daring mission. Okay, so moving on. So here's some other moons, Saturn, all very interesting in their own right. These are images taken by Cassini. So lots of interesting structures and features. Here's the rings from above. So during this event, actually, there were structures that were sort of emanating from the rings going vertically, and you can see them very clearly because they cast a shadow. And then I believe this is a moon called a shepherd that kind of goes in between the rings and gobbles up the material in there. So here's another view of the rings and the vertical structure. And the rings of Saturn, they're like a mini solar system. So you can get essentially over a long period of time, these dust grains and ice blocks, they sort of clump together over time, and then they sort of attract other smaller particles to come together. And this essentially was the birth of a new moon, and the astronomer based in Queen Mary University in London called it after his wife, Peggy, which is a good idea. So yeah, you can see it there. Okay, now really before Cassini, they built this massive probe for good reason. Voyager 1, sort of sacrificed its life because of Titan. So all of this attention was towards Titan. And there's still many open questions, and indeed there's a future mission to Titan. But really one of the big surprises was this very tiny moon in the inner magnetosphere of Saturn called Enceladus. Okay, so actually during the first few flybys, I don't quite remember the history well. I mean, this was before my time. It was seen as an interesting moon. There were speculations about it, but nothing out of the ordinary was seen. I mean, one thing that was interesting is that the surface was quite smooth, and there were very few craters. And that's actually quite an interesting clue to geological activity, because if something's been in orbit for millions and millions of years, like the moon, you'd expect it, based on probability, to be impacted a certain number of times and have a certain number of craters. But when you see fewer craters than you expect, that means there's some sort of rejuvenating geological activity beneath the surface. So a couple of flybys later, around Enceladus, a plume of water was discovered. A geyser was discovered in its southern pole. Now, actually, this image was taken after the discovery. So the way it was discovered was actually quite interesting. And actually, that's why it may seem like I completely changed topics, because I was talking about the solar wind and frozen in plasma. But here's exactly why. Okay. So here, if we're looking down on Saturn and we can see those lines that are emanating out of Saturn, that's the magnetic field of Saturn. So it is rotating around with the rotational speed of Saturn. Okay, so it's co-rotating with the planet. And here's Enceladus moving around in its orbital speed. So it's doing its thing in its orbital speed, but since Enceladus's orbital speed is less than Saturn's rotational speed, it's being continuously overtaken by Saturn's magnetic field. Okay, so we're looking down based on this scary eye. Now, if we look on from the side, essentially what happens is, now, if Enceladus were an inert body, so like our moon, the field lines would just go straight through. They wouldn't see it. Okay, it would be completely invisible to the field lines. But if there's some conductivity, some atmosphere, or some dynamism going on, some ionized plasma around the moon, then that will act as a barrier to the field lines. Okay, so this is where the frozen in condition comes in. So you can see that the field lines will take the shape of that barrier. The plasmas will become locked into it. So this essentially was the first clue that there was a source, that Enceladus was a source of plasma. Okay, that plasma must have been coming from somewhere, and that somewhere was Enceladus. A number of flybys later that went closer confirmed that, and only then did Cassini's cameras then point onto Enceladus and actually take those pictures. Okay, so the initial discovery was an invisible discovery that there was water coming out of Enceladus. So here's, yeah. Yeah, absolutely. Yeah. So I'll talk a bit more about that in a moment. But yes, so it was essentially discovered that Enceladus has a global ocean beneath its surface. Okay, and there are cracks on its surface, and due to the pressure, you essentially have the continuous jet of water that's being released. And then in the presence of solar radiation, that water gets ionized, it becomes a plasma, and then it begins to interact with the magnetic field. Okay, so here measurements of the magnetic field. It's very straightforward instrument, very straightforward data set. You're measuring a vector, so you're measuring an X component, a Y component, and a Z component, and then you're measuring the magnitude. Okay, so and you measure that continuously in Saturn's magnetosphere. But then close to Enceladus, you see that blip over here, and then obviously these there. Once that is essentially, once Saturn's magnetic field is subtracted out of the measured field, you're left with a residual, and essentially you get these perturbations in the field telling you that there's some interference going on. Now, how do we know? It's because we understand Saturn's magnetic field. We know that it should be pointing from north to south. And if Enceladus were just an inert moon, it wouldn't interfere with that north to south topology. But since there's something going on, you can see the field is being deflected, and that's because of the frozen in condition. Okay, so here's an artist impression of Enceladus. It has an atmosphere, and that's essentially because of the plume that's coming out of it that's being ionized. Some of that gets captured by its gravitational field to form a very tenuous atmosphere around it. And anytime a spacecraft flies past Enceladus, you'll measure this deflection in the magnetic field. Okay, so I put a thank you to plasma and the frozen in flux. Okay, further investigations were made. So looking at heat maps, so it was predicted that nothing really was going on at Enceladus, but actually when you look at it, you can see that there are hot spots in the southern pole. So that's where the jet is coming out of. And essentially, so these are known as tiger stripes. So there are fractures there. And essentially that's from tidal forces. So those fractures essentially expand and contract because the orbit of Enceladus is eccentric. Okay. And then actually, it's those tidal forces that keep the liquids beneath the surface of beneath the surface of Enceladus in liquid form. Okay. Now this has really ushered in a new era of looking for life, because for long it was thought we should look at the Goldilocks zone. So essentially, there's a region in any stellar system where if you're too close to the sun or the star, then water on the surface is in the form of vapor. And if you're too far away, it's in the form of ice. No, vapor. And if you're too far away, it's going to be in the form of ice. And there's somewhere in between, like where Earth's orbit is, where in the Goldilocks zone and water exists in liquid form. And liquid water is an ingredient for life. So it's one of the 4 ingredients. You need liquid water, you need hydrocarbon, you need a source of energy, and you need stability. Now, it's been discovered that obviously the gaseous planets can't have, an ocean, but they're moons. So even though they're so far away from the sun and they intercept so little solar radiation and energy, these tidal forces with the gigantic planets due to their eccentric orbit is enough to generate heat. And some of the rocks as well are also radioactive, so they emanate heat as well. Now, in addition to that, there's also ammonia that's discovered in these oceans. And why is that Why is that important? Why is the discovery of ammonia important in these oceans? Any guess? Not quite. Yeah, more specifically, ammonia compounds. So that's an antifreeze. Okay, so that lowers the threshold for freezing, and so keeps it in liquid water form. Okay. And actually, several passes went through. Cassini went right through the plume and sniffed some of the material that was coming out of it, and conducted mass spectrometry. And what they found were essentially hydrocarbons. Okay, so essentially, you have your liquid water, you have your hydrocarbons, you have your source of energy, which is not the sun, but it's internal heat and tidal forces. The stability question is still up in the air. So obviously, for life to evolve, you kind of need these systems to be stable over a very, very long period of time. Now, that's not obviously a slam dunk for life. It's just that these are the conditions that could lead to the formation and evolution of life. Okay, so moving on to Jupiter. So here we have an artist impression of the magnetosphere of Jupiter, and it is so large, as I mentioned, 100 Jupiter radii in the day side, that it engulfs all of the Galilean moons. So we have 4 Galilean moons. Those are the major moons of Jupiter, and their orbits are permanently embedded within the magnetic field of Jupiter. And each of these moons, they're really, really unique. So Europa is known for having an icy shell and an ocean beneath its surface. So this was discovered by the Galileo spacecraft in the early 2000s, I believe. Ganymede is a very interesting one. So Ganymede is the largest moon in our solar system. It's larger than Mercury. It's the only moon we know of that has its own permanent magnetic field. So if you are walking on the surface of Ganymede with your compass, you can find your way around. Okay. Now, in addition to that, Ganymede also has a subsurface ocean that contains more water than all of the Earth's oceans combined. Okay, so it's enormous. Now, there are missions on the way there. So next year, Europa Clipper is going to go to Europa and essentially fly past a number of times. And then JUICE, the European Space Agency's Jupiter Icy Moons Explorer, it's our first flagship mission. It's on its way. It launched in April, and it's on its way to Ganymede, to actually orbit Ganymede. It'll be the first spacecraft to orbit a moon other than our own, because so you already have 2 missions, 2 flagship missions, €1 billion, over €1 billion, over $1 billion, to the Jupiter system, and that's because of the emergence, the sort of new chapter we have in the question of habitability. Okay. And then this Callisto as well, also very interesting, has a dense ionosphere, also believed to have an ocean. And Io is a very, very volcanic moon. And so it is just continuously erupting, an extremely hostile environment. So there's hot magma beneath its surface. And actually the volcanoes to scale compared to Io's diameters are much larger than Everest. Okay. Now, speaking of the aurora, see this system, on one hand, it is so large. And if you think about the solar wind never comes in contact with Jupiter, but the solar wind is impinging on Jupiter's magnetopoles, which is 100 times its radius far away. So there's very little contact between the solar wind on Jupiter on one hand. On another hand, the solar wind at such far distances is really, 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 really tenuous. I mean, the densities are low, temperatures are low. So it isn't really a big source of energy input into the system. Yet, the most powerful auroras in the solar system comes from Jupiter. Okay, so how does that happen in the absence of a driver? There's an internal driver, and that's Io. So Io is continuously releasing material in the form of sulfur dioxide. So it's estimated to be 1 ton a second. And that sulfur dioxide starts life as a neutral gas. But then in the presence of solar radiation and bombardment with other particles, it becomes ionized, it becomes a plasma. Now, once it becomes a plasma, it becomes locked into Jupiter's magnetic field from the frozen-in condition and starts to rotate with Jupiter's magnetic field. And so it forms a donut around Jupiter. This is called the Io torus. Okay, it's actually a very dense donut in the innermost magnetosphere of Jupiter. Now, over time, you have this continuous loading of sulfur dioxide from Io, and these need to go somewhere. So over time, actually, they diffuse outward. So they diffuse away from Io into the middle and outer magnetosphere. Now, as they do that, they're conserving angular momentum as they do that. Okay, so there's no torque acting on it. They're conserving angular momentum, but they're moving outward. So as your R is increasing, if you conserve angular momentum, then your azimuthal velocity is going to decrease. So they start to slow down and they start to lag. They sub-corrotate with respect to Jupiter. Now, when they do that, because they're locked into the field lines then become swept back. They get dragged backwards away with the sub-corrotating plasma. You can see in the innermost, they're sort of rigidly in corrotation, but when you move away, they start to lag. Now, this deformation in the magnetic field, so from Ampere's law, in Maxwell's equation, it says that if you have a curl in your magnetic field, that's just kind of like a shear, if you like, in your magnetic field, it's going to give rise to a current, okay? And these are the currents that then travel along the field lines that reach the polar regions and generate the auroras, okay? So what carries these currents? These are the electrons that are carrying they're the charge that's carrying those currents. Okay, so it's really as a consequence of this, starting life at Io and then diffusing outward, and then the frozen end means conservation of angular momentum means they have to slow down. Frozen end means they have to drag the magnetic field lines along with them. Then Ampere's law says, well, if you have a shear in the magnetic field, you need to have currents. Then you have a system of currents that's operating all the time, and essentially you get these electron beams that are flowing along the field lines, and they crash onto the atmosphere of Jupiter. Okay, now let's see. Okay, so thankfully, I think this is a straightforward. Now, this is Juno, and this is Juno undertaking its polar orbit. So it's really neat. We're getting unprecedented views of Jupiter's poles, and that's kind of where the really, really interesting things happen. And it does a pole-to-pole pass each time it comes by Jupiter, and it takes images of Jupiter's aurora. And in addition to that, it measures magnetic field lines just above the aurora. And those magnetic field lines that are threading the aurora below, it's essentially measuring the fields and particles that are in action, that are accelerating the electrons to drive that current and essentially to generate the aurora. So, couple of instruments on Juno, so not too dissimilar from Cassini. You have a number of cameras. You have, this is a new instrument. It's a microwave radiometer. It's essentially to look for water content and ammonia content on Jupiter's atmosphere at different depths. And then you have the usual fields and particles instrumentation. So instrumentation that measures charged particles and electromagnetic fields. Electromagnetic fields are the source of energy that accelerate charged particles that then crash into the atmosphere and generate the aurora. So we're able to get a complete picture of how this process operates at Jupiter. Okay, so there are 4 themes for Juno. I won't go through each of them, but this is essentially the lens through which we're looking at it. So the magnetosphere and the aurora. Juno also plays a role in understanding the origin of Jupiter, the interior of Jupiter, as well as the atmosphere of Jupiter. Okay, so here's a close-up image of Jupiter's northern aurora. This is taken by the Hubble Space Telescope. And then essentially you can see that there's the band of light that's encircling the pole that we're sort of used to in Earth's aurora. But there are other very, very interesting structures. So one thing that's unique about Jupiter's aurora is poleward of this band is extremely dynamic and extremely bright. Okay, so in Earth's aurora, it's pretty much dark. You just see a nice ring around the pole. And we still don't understand how this is generated. It's still a really big mystery. And the reason why it's a big mystery is because once you go poleward, if you think about the magnetic field line that's threading this region, the more poleward you go, the farther out the field line goes, and we just don't know where that field line stops, okay? But when you're in the equator, those field lines map to closer distances to the planet, okay? Another uniqueness with Jupiter's aurora is that the moons, so Io, Ganymede, Europa, the Galilean moons, actually have footprints on the aurora. So essentially, these are field lines that are connected directly to Io's orbit. And the aurora rivals that of the main emission. Okay, so I'm going to fly through this because I'm going above time, but I will just, 2 quick slides. I just want to really answer the so what question as to why do we care about Jupiter's aurora? Now, you can see we have essentially a mosaic here. Before going into Jupiter's magnetosphere, we learned a lot about it from Hubble Space Telescope images, because those are essentially imprints of the processes that are operating in the magnetosphere. So essentially, it gives us the essential context to understand the dynamics of Jupiter's magnetosphere. Another is that Jupiter's atmosphere is actually very hot, and same with Saturn, Uranus, and Neptune. They're very hot, even though they're so far away from the sun, and they intercept a tiny fraction of the solar radiation that we intercept. So solar radiation cannot account for their temperatures. So Jupiter is about 4.5 times hotter than predicted by solar radiation models. So the Galileo spacecraft had a probe that was dropped into Jupiter and took measurements of the temperature. This is altitude. So you can see that these temperatures were much higher than what solar radiation models predicted, okay? And the reason for this is actually Jupiter's aurora. It's so powerful that it's a source of heat, okay? So that heat essentially heats up the polar atmosphere, and meridional winds then transport those towards the equator. So if you look at an infrared image of Jupiter's aurora, you can see a hot spot on the poles and then a smooth gradient equatorially. Okay, so I'm going to fly through these. I'm afraid I'm over time. And I will just touch a bit on these planets here. And essentially, sorry, these moons, I should say. And essentially, as I mentioned, we know that they have oceans beneath their surface. And what's really interesting was that, this was discovered from the Galileo spacecraft, from the magnetometer instrument. And what happened was, when that spacecraft flew past the moons, there were signals in the magnetic field that the scientists were able to infer an ocean beneath the surface. So how do they do that? Essentially, these oceans are in contact with rocks from the interior or the core. And so they're salty oceans, okay? And because they're salty, that means they're conductive. Now, how does that translate to signals in the magnetic field? Okay, so I'll just fly through this again, I'm afraid. So I mentioned that Jupiter's magnetic field is tilted with respect to the spin axis. That's not the case for Saturn, but that's the case for Jupiter. It's tilted. And so what you have is, when the planet rotates, the magnetosphere then wobbles. So it looks like this. So you see, Io is actually confined to its orbital plane. But if you look at it in Io's frame, Jupiter's magnetic field is wobbling up and down. And that wobble is a time-varying magnetic field. So if you have a time-varying magnetic field and a conductor, so the ocean is a conductor, it's then going to give rise to currents, okay? So this is Faraday's law. And those currents will induce a secondary magnetic field, okay? And that secondary magnetic field is then picked up in the signal. And from that, you can infer that there's a conductor beneath the surface. Now, how do we know that that conductor is not just an ion core? There's about 6 orders of magnitude in the conductivity between salt water and ion core. So that's quite easy to differentiate between the two, okay? And then there are also further evidence from that. That was the discovery. There are lots of water group ions that are measured in Jupiter's magnetosphere, and those are, their origins are traced to the interiors of these moons, okay? So I think I encourage you to read about JUICE, which recently launched. We are very excited, well, keeping our fingers and toes crossed to send a spacecraft to Uranus, which is the next on the list. So the National Academy of Science recommended an orbiter to Uranus as a priority. So we're hoping that NASA realizes this dream or this wish that we have. Uranus is very interesting because it's on its side. So you can see that's the rotational axis with respect to the ecliptic. It's on its side. So you can look at it pole on, but then there's an extremely large tilt. So its magnetosphere is just continuously tumbling. So we really have no idea how to handle this at the moment. It's actually very dizzying when we start to think about that. Okay, and then I will stop here. So thank you all.
Thank you very much. Does anybody have any questions? Of course.
You hinted the possibility of an ocean under, oh, sorry. You hinted at the possibility of an ocean under Titan's surface. And you showed the possibility of measuring that on Jupiter's moon, but on Saturn, without the tilt, how do you have evidence that there could be an ocean?
That's an excellent question. So there are two answers to that. Now, Enceladus, we know that there's a global ocean, but there's no tilt, okay? So the field doesn't wobble. So you don't have you don't have a time-varying field that's in the periods of the planetary rotation. But there's an orbital eccentricity, and the dipole falls off as 1/r cubed. So you do have a time-varying magnetic field just by being a little bit farther away and a little bit closer, but that's at the period at the synodic period, okay? So actually for Jupiter, you have that signal at the planetary rotation period and the moon's synodic period, but at Saturn, you don't have the planetary rotation period, okay? Now, Titan is very, very far out. Sometimes it finds itself in the solar wind because the magnetosphere of Saturn flaps back and forth. So it's difficult to make that analysis, but also what challenges this technique at Titan is that, as I mentioned, its atmosphere is extremely dense. It has an ionosphere and electrical currents flow in it, and that masks any signal that might come from beneath the surface. So there's just not that sensitivity to be able to tell. Yeah.
Excellent. I think there was one on the other side here.
For the missions, JUICE and the others that are going, how definitive will they be able to be about the nature of the organic compounds that we, and how definitive are we currently in our understanding of this? I mean, it showed from the graph just a bundle, but will there be instrumentation that would be able to analyze specific chemical footprints?
Yes, absolutely. Yeah. So there's next generation mass spectrometers. So I showed earlier those bar graphs. They only had the resolution to identify sort of much smaller molecules, like maybe methane. But when it comes to larger chains, that's actually going to be one of the key things for Europa Clipper. It has a next generation mass spectrometer that has that resolution and sensitivity as well to look at larger organic compounds. Because, you know, methane is a building block, and there are just so many permutations of chains you can get beyond that. And now it's all down to modeling and a bit of guesswork, but this will give us a real good observational constraint on that. Yeah. Thank you.
Hi, I know Iapetus also has some strange things going on, like one side is dark, the other side is light.
Yeah, that's right.
I'm trying to remember, where does that dark material come from?
Yeah, that's a good question. I remember sitting in a talk on that a couple of years ago. I don't know if it's ring material or something. Yeah, it escapes me. Yeah, but yeah, great observation.
Got one more over here.
Hopefully a simple question, but you might not know the answer offhand. If we determine the rotational period of Saturn and Jupiter by their magnetic or by their radio emissions, do you know what the particularly at Jupiter, do you know what the difference is between, let's say, the apparent rotation based on the great red spot or the atmosphere versus the radio emissions?
I don't know the number, but let me just make a point about Saturn. So the best estimate now of Saturn's rotation is from ring seismology. So it's looking at different modes from gravity experiment of the rings, and they were able to constrain what the interior rotation is, because the radio waves are not reliable, as I showed earlier. For Jupiter, I mean, the atmosphere has a viscosity, and so different layers slip with respect to one another. So invariably, the great red spot is slipping with respect to the rotation of the core. Yeah, but I don't know by how much.
Does Jupiter's atmosphere have differential rotation like the sun does?
Well, right. Okay. So presumably for the sun, you mean latitudinal differential rotation.
Yes.
Yeah. So yes, in addition to differential rotation altitude, yes, there are different zonal wind speeds. Yeah, you have, so if you look at a profile with altitude, yes, the zonal, there are bands essentially that move at different speeds. Yeah.
Thanks.
But the core is rotating rigidly. It's a solid core of Jupiter. Well, at whatever the rotation speed is. Yeah. Yeah. And so that's why the magnetic field give you a clue, because they're generated at the core. And so the idea is that they rotate.
All right. Do we have any online, Matt?
No.
Interesting. All right. Well, thank you very much. Appreciate your.
Thank you for having me.
It's
Thank you.
Yes, yes. All right. Well, that concludes our evening for tonight. We do have 2 announcements. We have some lost and found in the back of the room. And one of them is actually, which I'm going to show, so it might trigger somebody to remember that they left it at JJC. It is a white notebook with some interesting calculations of astronomy. So if this is yours, please contact us because we would like to get it back to its owner. And also Old Chicago, afterwards, we have tried to contact them and hopefully they have a reservation for us. So that way we won't be waiting all night for our beer and pizza. So, yes. Oh, Old Chicago, it is actually on the road right outside, heading west to the stoplight, east, east, 2 stoplights, just on the other side of Harmer Mall. Yeah, it's just a little ways down the road. If not, follow the caravan over there, people. So, yes, exactly. All right. Yep. Have a great evening, and I will see you guys next month on August 3rd.